Hello students, I am Sanjay Manghnani, Assistant Professor, Mechanical Engineering Department of Arya College of Engineering and IT, Kukas, Jaipur. In last lecture, we have discussed about the classification of the bearings. In this lecture, we will discuss some design concept and important terms related to the journal bearing. So for designing a journal bearing, the lubricant and its viscosity is very important point. The main purpose of the lubricant in journal bearing is to reduce the friction, losses and wear between the journal and the bearing surface. It also carry away the heat generated by the friction. All the lubricants can be grouped into three types: liquid, semi-liquid and solid. Liquid lubricants are mineral oils and synthetic oils. Semi-liquid lubricants are the grease, and solid lubricants are graphite, molybdenum disulfide and tungsten disulfide. Now viscosity. Viscosity is the most important physical property of oils. Basically, it determines the oil's load carrying capacity, thickness of the lubricating film maintained, and operating temperature of the bearing. Viscosity is the internal friction resistance offered by a fluid to change its shape. A high viscous oil can support heavier loads, but it has also more internal friction. We know that the Newton's law of viscous flow states that the shear stress in a fluid is directly proportional to the velocity gradient dV by dy. This is shown in this equation that shear stress tau in fluid is directly proportional to the dV by dy. Here Z is the absolute viscosity of the oil, whose unit is Newton second per meter square. These are the formula of absolute viscosity, kinematic viscosity, Zk. Here Z is the absolute viscosity, the unit is Newton second per meter square. Zk is the kinematic viscosity of oil, unit is meter square per second, and Z-K is the kinematic viscosity of oil, but the unit is centistroke. And the relationship between Zk and Z is given by the equation 15.2a, and the relationship between Zk and Z-K is given by the equation 15.2b of the data handbook of the Mahadevan. Here Zk is Z upon rho. Rho is the specific gravity at any temperature. It is given by the equation 15.3. Rho T means rho at any temperature is equal to rho at 15 degrees centigrade minus 0.00063 T minus 15. So we can calculate the specific gravity at any temperature of the oil. So how the viscosity is measured? Viscosity is expressed by the Seebold second. It is the time taken by the 60 ml of the lubricant at a specified temperature to flow through a tube 17.6 mm in diameter and 12.25 mm long, and this time is expressed as Sebolt second. This is the formula of Z dash K and Sebolt second S dash. So if we know the S dash, value of the S dash, then we can calculate the Z dash K. Z dash K is the kinematic viscosity in centistroke. So after calculating Z dash K, we can calculate the Zk by this equation, and then by Zk we can calculate the Z. Now how we select the oil for the journal bearing? In numericals, we will use the table 15.1 and figure 15.1 from the data handbook. In table 15.1 as shown, there are 11 types of oils for different applications. In figure 15.1, we can calculate the Sebolt second and also the kinematic viscosity in centistroke. In table 15.1, this is the specific gravity rho at 15 degrees centigrade temperature. So we can calculate the specific gravity at any temperature by this formula. In this rho 15, the value of rho 15 will be taken from this table. As shown in figure 15.1, at x-axis there is the operating temperature of the oil. Generally we will take the operating temperature of oil between 50 to 80 degrees centigrade. On y-axis there is Sebolt second on the left side and Z dash K on the right side. So first we select an oil from the table 15.1. Let me take the oil number 3 and we assume that the temperature of the oil is 60 degrees centigrade. So for this oil number 3, we will use this line number 3. So from 60 degrees centigrade and the line number 3, we can determine the value of Z dash K directly, or we can also find the Sebolt second. So this value of Z dash K, by determining this value of Z dash K, we will find the Zk and then Z. So this is the process of determining the viscosity of the oil. Now some important terms used in hydrodynamic journal bearing. The first is the radial clearance. Radial clearance is the difference between the radius of the bearing and the journal. Let capital D is the diameter of the bearing and small d is the diameter of the journal and L is the length of the bearing. So radial clearance is given by C is equal to difference between the radius of the bearing and the journal. So capital D minus D divided by 2. This is shown in this diagram. Small r is the radius of the journal and this is the diameter of the bearing. So this is the clearance C, radial clearance C. Now the bearing pressure. We know that the bearing pressure is equal to force upon area. Let the force is W acting on the bearing. The force is perpendicular to the axis of the shaft. So this is the force W. So what is the area? Area is the projected area of this shaft. So projected area, what is the projected area? Projected area of a cylindrical part is a rectangle. So area is the area of this rectangle, which is equal to 2r. This is 2r and this is the length of the bearing. So pressure P, bearing pressure P is equal to W upon 2RL. Now minimum oil film thickness. Basically it is the minimum distance between the bearing and the journal under the complete lubrication condition. As shown in this diagram, this HO, this is the oil film thickness. So this is the minimum thickness at any time. So HO is the minimum oil film thickness. In this diagram, O dash is the center point of the bearing and O is the center point of the journal. This E is the eccentricity between this O dash and O, and this is the radius of the journal, and this is the oil film thickness, minimum oil film thickness HO at any point of the cycle. Now next term is the Sommerfeld number. The Sommerfeld number is a dimensionless parameter which is used in the design of the journal bearing. Basically it is used for the calculation of the minimum oil film thickness HO. These are the formula of Sommerfeld number from the data handbook. We can directly use in the numerical, and this is the figure for a Sommerfeld number. In this, on the x-axis there is S means Sommerfeld number, and on the y-axis there is the value of HO by C. So if the value of S, Sommerfeld number, is known and C is the radial clearance, is known, then we can calculate the minimum oil film thickness HO. There are many graphs for the different angle of contact. Generally for full journal bearing, it is angle of contact is 360 degree. Let the Sommerfeld number is 4 into 10 raised to minus 6 second per minute. So this is the value of Sommerfeld number, and for a full journal bearing we can determine the value of HO by C. So from HO by C value we can calculate the minimum oil film thickness HO. So these are the some important points to design a journal bearing. In next lecture we will take some more design concept of journal bearing. Thank you.